In this video, I'm going to look at the surface area of a solid of revolution. We start by looking at a curve and rotating it about the x-axis. So let's take the curve, this red curve that's shown. If we rotate that about the x-axis, we will get a solid shape, and we're looking for the surface area between x equals a and x equals b. If we look just at this little section delta s, and rotate that about the x-axis, we will form a hollow disk or a hollow cylinder. The radius y and length delta s. So the area of that hollow disk will be 2 pi y delta s. And so that's what I've just said. And we're looking at the bottom here at the surface area of the disk is approximately 2 pi y delta s. The total surface area, therefore, is going to be the sum between x equals a and x equals b of all these 2 pi y delta s's. If we now let delta s tend to 0, this surface area is going to be the integral from x equals a to x equals b of 2 pi y ds. Well, let's look at the Cartesian case first. So for a Cartesian equation, the area is still the integral of 2 pi y ds, but in this case we want to do ds by dx dx. If we remember that delta s squared is approximately equal to delta x squared plus delta y squared, dividing both sides by delta x squared, 1 plus delta y by delta x squared. Now let delta x tend to 0, take the square root, ds by dx is equal to the square root of 1 plus dy by dx squared, something that you met when we were looking at arc length. So this gives us that the area for Cartesian equations is equal to the integral between x equals a and x equals b of 2 pi y ds by dx is root 1 plus dy by dx squared dx. Okay, now let's look at parametric equations. The area is still the integral of 2 pi y ds, and this time we do the integral of 2 pi y ds by dt dt. And in the same way, we start with delta s squared is delta x squared plus delta y squared, dividing both sides by delta t squared. We get what we saw when we were doing arc length. And if we let delta t tend to 0, we get ds by dt is equal to the square root of dx by dt squared plus dy by dt squared, which is x dot squared plus y dot squared, which gives us that the area is equal to the integral 2 pi y root x dot squared plus y dot squared dt. which I have summarized here. The area is always 2 pi y ds, and then you can convert it easily for Cartesian equations and for parametric equations. Now let's see how we can apply this to find the area of a sphere, radius r with centre the origin, between the two planes x equals a and x equals b. How can we find the area of that part of the sphere? Well, we can think of the circle x squared plus y squared equals r squared, rotated about the x-axis to form the sphere. The area that we want is the integral from x equals a to x equals b of 2 pi y ds. And as this is the Cartesian case, we're looking for the integral 2 pi y ds by dx dx. Now I can just write a and b because I've written dx. So we need ds by dx. ds by dx is root 1 plus dy by dx squared, so we need dy by dx. We have x squared plus y squared is equal to r squared. If I differentiate that, I get 2x plus 2y dy by dx is equal to 0, which gives me that dy by dx is equal to minus x over y. So ds by dx is what I'm looking for. That is the square root of 1 plus dy by dx squared, and that is the square root of 1 plus x squared over y squared, which is root y squared plus x squared over y, and that conveniently is just r over y, because x squared plus y squared is r squared. And so my area now, which is the integral of 2 pi y ds by dx dx from a to b, is the integral a to b. 2 pi y ds by dx is r over y dx. Well, this is now a nice easy integral. Let's do it on the next line. A to b, 2 pi r dx. 2 pi r is constant, so this is 2 pi rx from a to b, and this tells me therefore that the area is 2 pi rb minus 2 pi ra. So there is the area between x equals a and b. Well, if I want to go over the whole sphere, I would have to go from minus a or minus r up to plus r. I'd have to work from a is minus r to b is r. For the whole sphere, a is minus r, b is r, and therefore the area is equal to 2 pi r minus minus r, which is 4 pi r squared. A formula which you should know, and we've now proved it. On a historical note, Archimedes knew that the surface area of a sphere was equal to the area of a cylinder which immediately surrounds it. In other words, Archimedes knew that the area of the sphere is equal to the curved surface area of the cylinder. Well, we should know about a cylinder. The curved surface of a cylinder is 2 pi r h. H in this case is 2r. 2 pi r times 2r, 4 pi r squared, which agrees with the result that we just had. Now let's look at the surface area of part of a parabola rotated about the x-axis. We take the parabola x equals at squared, 2at, and we take the section between the origin, where t is 0, and the point P, where t is 2. We rotate this about the x-axis. Now find the surface area of the shape formed. Well, the surface area is always the integral of 2 pi y ds. In this case, we want the integral of 2 pi y ds by dt, and we remember that ds by dt is the square root of x dot squared plus y dot squared. So we're looking for x dot and y dot. We know that x is equal to at squared and that y is equal to 2at. Therefore, x dot is 2at and y dot is just 2a. So ds by dt, which is root x dot squared plus y dot squared, is root 4a squared t squared plus 4a squared, which is 2a root t squared plus 1. So my surface area now is the integral as t goes from 0 to 2. 2 pi y is 2at. ds by dt is 2a root t squared plus 1 dt. Give myself some more space. This is equal to, just simplifying it for the moment, the integral from 0 to 2. 2 and 2, that's 8 pi a squared, and we're left with t squared plus 1 to the half. Well, the bit that matters is t squared plus 1 to the half. This is like u to the half du by dt. So we are looking at, when we come to the t piece, we're looking at t squared plus 1 to the 3 over 2. If I differentiate t squared plus 1 to the 3 over 2, I get 3 t squared plus 1 to the half, so 3 over 2 t squared plus 1 to the half times 2t. The 2's cancel, so I'm just left with 1/3. And the limits are 0 and 2. And if we put that in, we get 8 pi a squared divided by 3. Putting t equal to 2, I get root 5 cubed. So that's 5 to the 3 over 2. Putting t equal to 0, I get 1, so that's minus 1. So 2 simple examples, one using the Cartesian equation and one the parametric.